Thank you. Hello everyone. I'm very happy and honored to be here today with you. So I will begin to start to talk about my work. So this presentation is divided into 4 parts. First, I will begin with some introduction, then continue on some performance assessment methods, and work on model implementation, and I will finally finish with some conclusion. So let's begin with introduction. We work on piezoelectric energy harvesting, and especially on increasing the coupling coefficient of the harvesters. Here on the right, you can see for purely resistive load, which is optimal, the normalized power to the normalized frequency. And you can see that by increasing the coupling coefficient, you increase also the maximum power, the limit power, which is given up to the mechanical quality factor. So this is quite a good graph to explain our work, because it explains for us the two very important factors here we have, the mechanical quality factor and the coupling coefficient. So we need to increase this coupling coefficient, and for this we can work on material and design. For the material aspect here, you can see a graph with the mechanical quality factor by the mechanical quality factor, by the mechanical coupling coefficient here. We can see that there are some point clusters here, the lead-based, which are PZT, like the best, maybe the better material for piezoelectric energy harvesting, and here some point for lead-free piezoelectric materials. And here there is a line that describes the power limit we saw earlier, and we saw that relatively to the lead-based materials, KN and lead-free are more near to this line. We want to be higher than the line. And because I work with lead-free materials because of hazardous characters and behavior of the lead-based materials. We saw earlier the global coupling coefficient, and it is proportional to the material coupling coefficient. So we need to ensure a high material coupling coefficient, and to do this we can have different exposures, which are here. Here you have the transverse mode exposure, which is achieved when the material is as a mechanical load perpendicularly to the polarization. And for this transverse mode, there are several hypotheses possible. Here is the wide beam hypothesis and the long beam hypothesis. For the wide beam, the coupling coefficient is higher because there is no lateral strain in the piezoelectric layers. And to improve this again, we can use the planar mode, which is the same as transverse mode, but omnidirectionally. And here again, the coupling coefficient is better than the wide beam hypothesis. So we want to achieve the planar mode exposure, but for this we need some design solutions. It can be done by auxetix structures. Auxetix structures are lattice structures that permit to get negative Poisson ratio. And there are 2 types of here auxetix structures, or reentrant honeycomb and chiral lattice. And we focus here mainly on reentrant honeycomb because they are better on negative Poisson ratio. Because as you can see here on this graph, the lattice Poisson ratio of the auxetix structure for the negative theta here can be down to -8, -10, dependent on the design of the structure. So here we have some auxetix structures, and there are 2 cases to use this on piezoelectric harvesters. The first case being the energy harvester with auxetix substrates out of resonance. Here we have a work done by Lee et al. In 2017. They used an auxetix substrate made of steel with polymer material. You can see that they explain the power increase here in the piezoelectric element thanks to some stress added to the piezoelectric layers. And so they give this equation saying that the maximum power is proportional to the squared stress. So here it looks quite relevant to by adding stress we add power. And in another case, we can use heat under resonance, as we do here. Here we compare two substrates. One is plane and one is auxetic. We can see the inverted displacement. And these authors, when they compare two auxetic substrates together, they found a better power, but not proportional to the squared stress here. So, invert proportional to the frequencies. So here we can see that in some cases, auxetic harvester should not be assessed with power output because it's not always a good point. And as I said earlier, there is some power limit for auxetic harvester under resonance. And this power limit is given by the invert frequency, is dependent on the invert frequency. And we can see here that it really fit this equation with these results. So the authors may have achieved the maximum power they could with auxetic substrates here in both cases. So our question would be, okay, so we want to use auxetic substrates to increase the coupling coefficient, so how can we process that and how can we do that? Because increasing the coupling coefficient, other than the power, would be good to increase the bandwidth, the frequency bandwidth of the harvester. So let's get into the performance assessment method. So here I give the elastic energy to introduce the subject, which is given by the elastic energy, the sum of elastic energy in the piezo element and the sum and plus the elastic energy in the substrate. We can see here the global electromechanical coupling coefficient, and as I said earlier, it's proportional to the material coupling coefficient linked by the energy ratio. So our method would be to get this coupling coefficient, the global coupling coefficient with the resonant frequency on finite element simulation software, and also the energy ratio on the software, so we can just have information on the material coupling coefficient. So here is the process we use. So first we design an harvester. We can assess it, we can compute it on finite element simulation software, then get some global coupling and material energy ratio to get the material coupling coefficient, and with some analysis on strain stress distribution and some to understand how it works, we could again increase have a better performance. So let's see some implementation of this model on our work. So here is the material we use for the implementation. As I said, we use lead-free materials. Here is a material supplied by the industrial Nitera, which is a Japanese industrial for piezoelectric ceramics. And we can see that this material has promising performance. Here is a prototype we designed without auxetic substrate system, just a simple white cantilever. So as I said, it's a white cantilever, so we may think it will have a good coupling, material coupling coefficient, as I said before. And we observed that by adding a gap here between the clamping part and the piezoelectric layer, we observe a decrease on coupling coefficient, global coupling coefficient, and we might want to know how this decrease happened. So here is the elastic energy ratio by the material electromechanical coupling coefficient. So the idea is to have some isolines here that describe the global coupling coefficient, and for each dot of these lines, there is like a couple of elastic energy ratio and material coupling. If we had here the experimental value of the global coupling we measured, it's around 8%. So we may want to have, by computing the values on the finite element software, some values on this time. Here are the results. So here we observe the evolution of the values of energy ratio and coupling coefficient for a different gap, the gap increasing as the dot decreased here. And we see that the more we increase the gap, the less energy we have, but the exposure remains the same. If we compare it to the theoretical values we had earlier, here is the long beam, wide beam, and planar mode. We see that we are over the long beam coefficient, but lower than the planar mode. So we would like to have these results in this orange part. Let's now work on some auxetic substrates. Here are two substrates. One is just hollowed out, and one is auxetix. They have the exact same field area. So this is to know if the performance change is only due to stiffness decrease. So stiffness decrease meaning frequency decrease, so better power. Here are the results. So first we studied on actual mode resonance. As we can see here, the auxetic property, as we have expansion, we expand laterally. Here are the results with the piezoelectric layers. So we see that on field substrate, we have a kind of displacement, which is inverted for the auxetic substrate. We have to note that it was really hard to get auxetic behavior on the piezoelectric layers because of the piezoelectric stiffness. And here are the results, values. So we see that the global coupling really increased by changing substrate, so did the energy ratio, but not the material coupling coefficient. Then on bending resonance mode here, so we don't see anymore any auxetic behavior. And at the same time, on the results here, we see the global coupling did increase for the hollowed one, but did not increase for the decreased for the auxetic one. The energy ratio did increase between the field and the hollowed, but not so much with the auxetic one, inversely to the previous one here. And the material coupling here decreased with the hollowed and auxetic substrates. So let's get to some conclusion. So as a result, we saw that the material coupling coefficient can be improved by exposing the material to planar mode. The material coupling coefficient can be computed using finite element simulation, but there are still difficulties in designing working solutions with auxetic substrates, and more investigation is needed. The further work here will be to work on auxetic design to achieve the planar mode and expand possibilities for bandwidth and or power output. Thanks for listening, and this work was supported by the National Agency for Research at the SIM laboratory in collaboration with IMS laboratory. Thank you.
Thank you very much.